Hello, everyone. My name is Dina Fusco, and I am the Vice President of Programs for the Stratford Chapter VFS. I would like to thank all of you for joining this virtual presentation featuring Professor Marilyn Smith, who will be discussing methods of aerodynamic modeling that impact the eVTOL industry and vertical flight applications more broadly. If anyone has any questions during the presentation, please put your questions in the question panel section, and we'll ask them at the end of the presentation. I would like to first introduce to you all Dr. Brian Wake, Lockheed Martin Sikorsky Technical Fellow. Dr. Wake received his PhD from Georgia Tech School of Aerospace Engineering in 1987, and then joined the United Technologies Research Center. After 30 years at UTRC, he moved to Sikorsky Aircraft, Lockheed Martin in 2017. I would like to now turn it over to Dr. Wake to introduce to you all our guest speaker this evening.
Thanks, Dina. Good evening, everyone. Thanks for joining us for this webinar. Yes, it's my pleasure to introduce our speaker, Dr. Marilyn Smith. Dr. Smith and I were actually in school together at Georgia Tech when we were both working on our master's degree in the School of Aerospace Engineering. And at the time, she was employed by Lockheed Corporation. She was working at the wind tunnel there as an engineer in Marietta, Georgia. She worked at Lockheed for about 10 years before going back to Georgia Tech to work towards her PhD. And then fast forwarding today, Dr. Marilyn Smith is a professor in the Daniel Guggenheim School of Aerospace Engineering at the Georgia Institute of Technology, and she's the director there of the Vertical Lift Research Center, which includes the Army, Navy, NASA Vertical Lift Research Center of Excellence, also known as VLRCO. Dr. Smith performs research in the areas of nonlinear computational aeromechanics, unsteady aerodynamics, for which she has over 200 publications and won multiple technical awards. She is a fellow of the AIAA and the Royal Aeronautical Society, and she is a technical fellow of the VFS. After numerous VFS leadership positions, she's currently serving as a technical director of the VFS. So with all that, and of course there's much more on our very impressive resume, but I think we want to go to our presentation, which is about dual solver hybrid methods for rotorcraft aeromechanics. So with that, Marilyn, go ahead.
I have to unmute myself. Thank you, Brian. It's been a long time, and I appreciate the fact you didn't mention what years it was that we were in school together. I don't admit to being that old, but I thank you all very much for inviting me tonight to give this presentation. It's going to be based on a paper that I just finished writing for the Aeronautical Journal. It's coming out in January. It's their 125th anniversary edition. So this invitation came right at the right time. So next slide, please. I'd like to dedicate this talk to Alan Egoff. Many of you know him. He's retired now from Sikorsky. But a little over 10 years ago, he challenged me to take on this problem. He went through and said some of the problems that he was having and what he would like to have. And it's taken a long time. It's taken a lot of different funding sources and a lot of different students. But I think we're really here. And so I want to dedicate this specifically to him. Next, please. So what's the point? We have a lot of different computational solver options that we use today. You know, the traditional computational CFD is very high fidelity. We can get a lot of the details of the physics. Unfortunately, it's expensive. And a big problem is that when we have issues such as we're trying to model hover, we're trying to model interference, interaction effects, the weight dissipates very quickly. So, you know, in order to make that go away, we have to put in more and more points, go to higher point solvers, which may mean going to a structured solver as opposed to an unstructured solver, which costs time to do meshing and so on and so forth. One recent experience that the Army had was that they were redesigning a component. They spent over 6 million hours on the DoD HPC over several months. I know industry certainly doesn't have that kind of computational resources. Now, we have other solvers. There's vorticity, velocity transport methods, originally developed by Richard Brown in the UK. There's also versions of that use meshes, which is what Richard started with, and they have also particle methods now. We have ART has developed a nice solver there. We also have potential methods. Now they're low cost. The problem is that they don't capture complex viscous aerodynamics very well. So we thought that hybrid CFD free wake methods would bridge the gap in cost and fidelity trade-off. Now, it's not new. When Alan challenged me to this wasn't a new idea. We did have what I like to call first generation hybrid methods out there. And when I'm talking about the hybrid methods tonight, I'm going to talk about CFD plus some other solver. And I'm not going to talk about a solver like in Helios, you have the CFD near body solvers, and then you have SAMCART. I'm not going to talk about that. I'm going to talk about different solvers other than URANs. Now, the problem is that these previous methods like this, they have trouble predicting, blade pitching moments and structural loads. They were also geared specifically to do a single blade, which has problems in and of itself. The second generations needed to be able to fill the current needs for production use. The prior methods were designed for academic use. Academics all have their own little in-house codes that they use for various things. I have my own for developing turbulence models and active flow. But when we talk about transitioning this to the community, academic versions just don't fill the gap. There are problems associated with it that if you're trying to use an industry, you can't follow behind and clean up behind whichever graduate student was working on the code the last time that it was touched. Next slide, please. So let's look at what a dual solver workflow should look like. So on the left here, you see we start with a potential wake, and we should be able to go up in fidelity as we go from the yellow all the way up to the blue to pure URANs. Now between there, depending on what you're trying to do, whether it's design or full up analysis, you may choose different versions in the hierarchy. So, for design, you may want a panel method and potential wake, and there's people out there who've been working on this. Then there's URANs with a potential wake, which can give you more of the analysis side, but again, it's going to still cost more than just the panel method. Then finally, if you have wakes or problems where you have a wake that needs to be resolved through an Euler or Navier-Stokes, say for example, the wakes between wind turbines on wind farms or flying in the ship air wake, then you might want to have as your wake solver a different Navier-Stokes solver, not something like a URANs, but something like the vorticity velocity transport method, which is designed specifically to not dissipate the wake. And then finally, you have URANs, and you're limited there only with how much computer time and memory you can stand. Now, these cannot be alone. I mean, I tell everyone, I tell the students that the days of doing CFD for CFD's sake is done. We are a multidisciplinary society today, and goodness knows when we talk about vertical lift, we live in the aeromechanics world. You cannot look at just CFD alone or aerodynamics alone. So your framework has to be able to couple with other codes, whether it be structural dynamics in order to look at aeroelasticity, acoustics to understand the noise problems, a 6-DOF if you're trying to do like a slung load, and then there may be other engineering tools such as survivability and things that will be fed by the CFD results, usually the near body CFD results, but you need them. And so we need to be able to have a workflow which can handle all of these. Next slide. Now, talking about that, we also don't want to look just at rotors. You know, some of the early solvers were just based on rotors, but we need to look at the vehicle holistically, whether we're talking about vehicles that are existing, and I put my favorite helicopter of all time, the Black Hawk UH-60 up in the upper left-hand corner. So you see, you know, that has rotor blades, it has a main rotor, it has a tail rotor, it has a fuselage. In the lower right, you'll see external cargo through, slung loads. If we're validating against wind tunnel data, we need to be able to model the wind tunnel. And of course, you know, we have our lovely hubs that are always a good thing to try to model and to get the drag right on. Now, we're also in probably one of the most exciting times for vertical lift since our whole industry started about 100 plus years ago. And that is, we're working in areas of future vertical lift, such as the Sikorsky proposal in the lower left, as well as urban air mobility and advanced air mobility, an example of which is the NASA Lift Plus Cruise configuration shown in the upper right. Now, those add even more complexity. So we need to be able to do coaxial rotors. We need to be able to do multiple rotors. We need to be able to solve traditional fixed wing components, such as propellers, wings, and maybe fuselages that aren't the more helicopter-like. You know, at some point, where do we transfer from having equivalent flat plate drag to drag counts? But our methodologies need to be able to handle these things, so they need to be quite flexible. We need to be able to do vehicle components, our current conventional vehicles, and then the new innovative vehicles of the future. If we don't have a dual solver that can do that the same way that a traditional CFD solver can do that, and the lower fidelity solvers can do that, then they're not really going to be useful, because their application range is far too small for today's current technology. Next slide, please. Now, we also have the requirements for production methodology. You know, I mentioned before that our early versions were academic, but what we need is we need to have solvers that are maintained and not by an academic institution. I would not want to use my in-house codes without having some tracking on there, which we do internally, but it's still hard when you're giving it out. And we call those trustworthy codes. So for example, the NASA Overflow, NASA Fun 3D, the Helios suite of codes, commercial codes, RCAS, the CDI codes, CHARM, the ART VVPM code. Those are trustworthy because they're being developed commercially. Okay, so we have either the government sponsored codes, which if you have looked into what they do, they are very good. They are research codes, and they usually are free if your use case is appropriate enough, but they are maintained to what I call a professional level. So if you have codes that are maintained and are trustworthy so that you can use them straight out of the box without having to check to see what someone has changed, then we call that a carefree application. We also want to use solvers that are approved by our sponsor or the authority for certification, like the FAA or EASA. Now, you know, that latter part is an ongoing issue because we're all talking about certification by design or certification by computations. But again, the codes that I mentioned for CFD are those exact codes, as well as the low fidelity codes. We also need to have them integrated into existing frameworks, such as, you know, for future vertical lift, the Army wants the vendors to use Helios or another Create AV tool suite. So you need to be able to integrate them into those existing frameworks. You also want to have solvers that are already in your production workflow. You want to minimize your learning time for your employees, and you want to be able to reuse meshes and input files. So these are all of the things that you need to think about when developing a workflow for a dual solver hybrid approach that is actually going to be useful in today's climate. So next slide, please. Now, this is one example of a dual solver hybrid code. This is actually Overflow plus Charm, which is one of the ones that we're doing. The first part of the seminar tonight is more general, and the second part, where I do some applications, are typically going to be most of my own. But you see here, what we want to do is we want to use the best characteristics and the native capabilities of the two solvers that we're coupling together. And then what we need to do is write coupling routines. Our goal at Georgia Tech is to develop coupling routines that can be used across a suite of these tools. In other words, the coupling routine, the APIs, we're writing them all in Python, and you'll be able to use them as long as your codes have the right APIs. And the people we're working with, Overflow, Fun3D, the CDI folks, and we're reaching out to ART to see if we can use the same kind of coupling routines. But here you see, you know, you just need a few inserts. You leave the major codes alone, and you work on only the coupling part. Now, the coupling part, again, I've been very vocal here about the fact that you don't want to use an academic code, and that's true. We're not going to use an academic code. The coupling code, but while being written here, is not going to be maintained by us. Currently, it's going to be given to NASA for the external one, CDI for their codes, and we already have something which I'll mention later in Helios, which is going to be upkept probably by my student who did it, because he's going to the Navy. So next slide, please. Now, there's two kinds of domain approaches that you can take with a dual solver hybrid code. The one is very much like the prior first generation code. So here I'm showing the S76 rotor. It's got a hub, and these are actually the meshes around them. So the blue box is the single blade option. So it just solves a blade. Here, that can be very, very advantageous if you're doing, say, for example, a hover calculation, and you don't need the entire vehicle. So if it's going to be very periodic, then you can take your single blade and you can write it however many blade times. In this case, you know, there were 4 blades. So you can rewrite it 4 times. The fact that it's axisymmetric, you take advantage of that. And so it cuts your time down from your typical CFD code to, you know, almost 90%. The trade-off is, of course, that if you need other characteristics, so such as the hub, or if you're doing things that are, or flight conditions that are not truly periodic, which a lot of them, even in level flight, are not, then you need to be able to do a full configuration, that is the entire rotor and whatever it goes. So rather than using something very complicated, I'm using here, again, just the S76, but this is just a very small portion. You could still add fuselages, tail rotors, and so forth to this. Here we have 2 different approaches. There's a contiguous approach where you model the blades and the hub, those are shown in blue and red. So those are highlighting those meshes. And then you encapsulate it into a near body background mesh. So you still have, if you're familiar with Overflow, you would still have like a level 1 mesh, but it would be much sparser than it is now. Okay. Then you also have another approach, which is faster, and that's called the non-contiguous approach. So the grids are not contiguous to one another. So in this case, the CFD solves only the meshes in blue and red, and there isn't any near body background mesh. So the second solver, the wake solver, actually passes the information back and forth between these different boxes. Now, the trade-off is with contiguous, of course, you're going to have more CFD points, so it's going to cost more. But what is nice is that defects, if you will, in your solver will be less apparent, and that's because your outer boundaries are farther away. And so we think about Biot-Savart law, vorticity inducing the velocity on these components. They're farther away. They're still important, but differences are going to be somewhat washed out because of your CFD grid. If you use a non-contiguous approach, then that tells you that any issues, any small errors that you may have in your coupling approach are going to be seen a lot more on the actual vehicle. Again, because of Biot-Savart law. Your background, your let's say, for example, your potential wake is much closer to the object, to your rotor, for example. And so the impact there is going to be much stronger. So you don't have the CFD wake to kind of dissipate even that small amount. Now, of course, the non-contiguous is much cheaper because you don't have to have even that level 1 wake. The other thing is when I show these near body meshes, we have found that you don't need to have as refined a mesh that you do for your full CFD. Now, that you have to take with a caveat because it depends on what you're trying to do. If you're doing something in the normal range of your flight envelope, kind of in the middle, you're not at one of the ends, then you can usually get away with reducing your mesh significantly. However, if you're at one of the pain points, for example, a very high thrust on the high speed, although not so much with the high speed, if you have dynamic stall, then you still have to be careful because your meshes in the CFD need to be able to capture that. So there's a bit of trade-off that goes on here. Next slide, please. Oh. Okay. Now, the interchange of information across the solvers is very important, and there's two ways to do that. One is known as a field velocity approach. This is very much like how we do moving motion in our regular CFD codes. Now, here for the field velocity approach, you can overwrite the induced velocities from the wake solver to the CFD solver. And you can see in this picture here, the CFD domain is in green. The charm wake vortex, you can see that they're superimposed. Okay, they're always superimposed no matter which approach you try to do. Now here, you can take that induced velocity and you can, write it at every mesh point, and the CFD solver will react immediately. The problem is that, you're writing this to potentially millions of mesh points. And you're doing this at a lot of time steps because it takes a number of revolutions, even if you're doing a loose coupling analysis here. Now, the boundary condition approach is that you do the same thing. You overwrite the induced velocities from your wake solver to your Navier-Stokes, but now you only do it on the boundary mesh points. The CFD solver takes a little bit more time to react because the updates have to propagate inward across all of the boundaries, but you have a much smaller fraction of mesh points involved. So you only need to overwrite, we've estimated somewhere between 0.9 to a contiguous mesh, like for a rotor, to up to 3% if you're doing non-contiguous and you have multiple rotors, a hub, and a fuselage. So you can see that savings is quite dramatic. It may not be much at one time step, but you add many, many time steps as you do all of your revolutions, and that can add up. Now, both approaches, you've got to be very careful not to double count the induced velocities. And that's part of what some of the dual solver codes that are out there, they simply just slam them together and they don't worry about the fact that they're double counting, because that's even more calculations that you have to do, because you have to subtract that from your CFD code. And so those are more calculations. So a lot of people haven't done that. The other thing is that you must ensure that your boundary conditions are handling the coupling properly. So whatever the, if velocity is going out versus velocity coming in, it needs to be that way when you do the coupling. Now, you might say, well, that's not a problem because I've got characteristic boundary conditions. The Riemann boundary conditions should take care of that. Well, we did find that there was some sensitivity to that. And to do that, I've got a slide next to show you. But here, what I want you to do is on this figure to the right, you see in purple, this outflow region. This is the region we're going to look at in the next slide. Next slide, please. Okay, so first of all, let's just look at the actual behavior here. And so you see that you have the blade tip vortices and the vortex sheet in green. You actually see that there is some inflow and outflow. So the vortices are coming out, but there's some red, I'm sorry, the green. Yes, the green is going out, the red is coming in. So there are some reddish pink areas where you've got some vorticity coming in from the other wake solver. Now, if you use the standard characteristic boundary condition, hit next, please. Just hit the button, it should come, there you go. So here's the standard Riemann boundary condition. And if you compare the middle slide, the middle picture to the one on the left here, you'll see that that looks pretty different. And so, and in fact, you see that this inflow outflow region boundary, you get a lot of non-physical vorticity being added. Now, that dashed line is just where we showed the region that's being inflow versus outflow. And so that's not something that we specifically designed, that's just highlighting that area. But that's what you get if you just use a standard Riemann. Now, we refactored this and we came up with the last boundary condition. So click again, please. All right, here we go. And so we have this new modified boundary condition. And if you compare the one on the right with the one on the left, you see that it duplicates the behavior that you see. Now, this modified boundary condition then replicates the actual physics that are going on between the two codes. And so this is important. And this is one of the things that I was really pointing out, that if you want to bring your boundaries in very close to your actual solid surface, this is going to become more and more important because of the Biot-Savart law. So next slide, please. Now, the other thing is interpolation. One of the things that we take advantage of when we're doing aeroelastic coupling, as well as this coupling here, is that the lower fidelity codes typically don't need the small time steps that the CFD code needs. So there's no need to run them at the same small time step. You can let them run in their own native capability, whatever is best for that. And then we can update at every time step for the larger time step case. So here, for example, here is, again, Overflow plus Charm that demonstrates this. So you see the green line at the left. So the CFD is running from 0 to 5 degrees, just taking whatever the data is. The data was at 0 degrees from Charm, and it's just using that over 5 degrees. It's not being updated. And then at 5 degrees, Charm does an update. This is a 5-degree step. And then, the boundary value changes, and it's a step function. And unfortunately, what it does is it introduces a lot of oscillations. And you can see this in the picture to the right. Now we want to add interpolation. And what many people have been using is what we're calling the velocity predictive interpolation. In other words, you use the velocities that are equal to the velocities, the induced velocities from the prior revolution, with the idea that as you go closer and closer to convergence, those are going to get smaller and smaller, the differences are. Well, that's a good approach. And again, if you're farther out, there's not as much problems because again, you get to dissipate some of the problems. But one of the things that you notice, and this is in blue, is that you're integrating from 0 to 5, but you're not all the way up at the top, okay? And that's because there is a change, and that delta, you'll still get oscillations. Now, they're not as bad as if you have the oscillations without interpolation, but they're still there. Now, the new approach that we've developed is to use what my student likes to call force predictive interpolation. So he calculates the velocities that are estimated from the forces of the most recent blade passage. Now, it sounds like it might be the same, but what you're doing is you're basically then estimating what the next velocities are going to be. So you have the prior one, the current one, and then the future one. So it's a future predictive approach. And when we use this, we find that we get results that are illustrated notionally by this orange line. And that is, we don't see that delta there. And so you see that when you turn on the interpolation, as we've done in the plot to the right, you can see the change just in the thrust coefficient. Then all of those oscillations that are, again, non-physical, they're just due to the updates from the solver, the Charm code. They basically go away. And so, you don't have to wait for multiple revolutions or multiple coupling iterations for it to settle down. And this is important too, because you can look at the convergence and estimate the convergence much more accurately. So next slide, please. This slide here is when you're talking about potential wakes. And we demonstrated this, or we didn't demonstrate this, but we found that this became an issue when we were working on the AIAA workshop for integrated propeller prediction, otherwise known as WIP. And so that has a propeller which is encapsulated in this hemispherical CFD mesh to the left. It's got color contours there, and then you can see the Charm code, the vorticity coming out, and we modeled the wing and the nacelle using Charm panel methods. But what we found is that if we didn't include the dφdt term, then we had much greater errors in the estimate of integrated propeller thrust coefficients than if we did our unsteady pressure. Now, the thought is that you don't really need this because your time steps are pretty small from the CFD side. But again, because even though you're interpolating and everything, you still need these these extra terms. So we've added it, and it's part of our coupling approach, because we take the charm outputs and we calculate this change in the velocity potential phi with respect to time. And so we add it to our pressure calculation, and then it perturbates through to the density. Now, as you see here in the chart below, you'll see that, you know, your percentage error with respect to overflow alone is fairly dramatic. So the middle one shows that we have a 2% error. That's neglecting that unsteady term. But if we have the steady term, the unsteady term added, we're within 0.3% of what was predicted with overflow alone. So when you have these highly unsteady interactions, this becomes important. Next slide, please. Okay, now that kind of ends the part where I'm just discussing about what are these methods. Now, if you want to use them, why should I take on a new solver? Why should I take on this? Because, you know, my workflow, my work days are already immense as it is. Well, let's look at how good they are. And so here's some applications. Next slide, please. There we go. So hover, we did some work with the S76 hover workshop, although I do note this is before we got some of our new improvements, so we actually expect it to get even better. But here what we're doing, we're comparing our ability to calculate the figure of merit, and we're comparing with, we used Overflow, and we're comparing with Rohit Jain's, the Army Helios calculation. Now, again, he's from the Army. He's got that beautiful HPC DOD time. And so it's really great because now the Army, in particular, Rohit, and up until recently, Mark Potsdam, since he retired, we're generating what I call the limit of what we can do with CFD. So they're using huge meshes, and they're giving us a good idea of what actually can be accomplished with CFD. Now, Bob Narducci did the second one, and he did more of what I would consider to be a production level solver. So, you know, Rohit used 448 million nodes, whereas Bob used 63 million nodes. We used different versions of Overflow Charm. One was the contiguous, so that includes the background meshes. So we dropped it from 63 million to 28. If we did the non-contiguous, we did 2 meshes, non-contiguous. We did what we call the full grid. So we just cut away all the background grids, and that was 15 million. And then we reduced it again to 9 million. And so the only thing that we found was that with the reduced mesh with non-contiguous, we ended up running it a little bit more. So, you know, 6 of one, half of the other. And so you see the cost ratio. And how does it do? Well, I give you an example for the swept tip blade, and, you know, caveat, that was our best one. We had problems with some of the others, but that problem seemed to be from differences from charm and overflow. In other words, other people using charm alone and with overflow alone also had those problems. So we don't think it was the hybrid part. But what's important to note here is the experiment are in black symbols. The industry overflow alone is the green line, and the physics limit for CFD are the green upside down triangles. So you see there is, we can actually estimate figure of merit within a very small delta within, of course, you know, experimental errors, but that requires a huge mesh. Now, if we use the production level mesh, something that, you know, is really realistic, then we get the green line, and we're off more than we'd like to be. So let's look at the red circle and the blue dots. So those are the approaches with the dual solver. And you see that we fall somewhere in between the two. Now, interestingly enough, at low thrust, we match more the industry level grid. But as we go closer and closer to stall at the higher ones, we actually are approaching then the Helios, the large grid. We see that the non-contiguous does have a little bit of a reduction, so a contiguous mesh may be appropriate when we're close to stall. That's one of the trade-offs you have to look at. And then on there too, I didn't mention, but there's gray squares, and that's charm. I'm not going to make any comment about the fact that charm falls on top of the experimental data. That's always something that we're always talking about. But again, this was run by somebody from CDI. So he knows everything to turn and what knobs to turn to get it exact. So I'm not going to guess how good my own charm analysis would be. Next slide, please. Now, we also looked at how we do with the physics and the estimation of integrated quantities in and out of ground effects. So here's an out of ground effect. So we've got, this is a micro rotor, by the way. It's not a full scale. So this is different Reynolds numbers than we're used to dealing with, unfortunately. But you'll see overall that the experiment is smoke in the left. The 2 CFD, the middle one is overflow alone, the right one is overflow charm. We have some differences, but one of the things I want you to notice is that when we're looking at the flow fields, we found that it was best visualized by doing velocity magnitude with a Q criterion overlaid to be able to pick out not only the slipstream and contour effects, but also to look at the vortices and the fact that you can have vortices pairing up and everything, as I'll show you in a minute. The slipstream boundary, we estimated it using the same kind of estimation that they used in experiments. I wouldn't put too much there because we have some, when we did the calculations, my student didn't take anything out because we wanted to really be very transparent with this, but you can see at the bottom of the 2 CFD pictures, that's where the starting vortex is. So we probably really should run it out a little bit further there. But in any case, what you see is the vortices from the CFD look, they're there, but you can see the dissipation. Whereas using the same near body mesh for the blade, and this, by the way, was a single blade, and we're using then charm in the background, you'll see that you're picking up a lot more of the artifacts. Now at the bottom, you'll see that charm becomes very unsteady at longer wake ages. And so this is why I say don't look so much at the at that slipstream, because really if I were drawing it just by eyeballing it, I could throw that out and we would see that the overflow charm slipstream boundary, which is the solid line, actually would look right on top of the others. So, and what's interesting is you can actually see the beginning of some vortex pairing here, which you see also as it comes into for the experiment. Now, this is more readily seen in the next slide. So if you can go to the next slide, please. We're going to be in ground effects. So we're at 2 rotor radii above the ground, and you'll see again, left is experimental, middle is overflow, and right is overflow charm. Now again, you see the same things that are happening here. You can see some vortex pairing. You don't see much with the overflow alone, and you can capture a lot more of the details with the overflow charm. And you'll notice again, until we get to the point where we start breaking up at the bottom, the slipstreams are pretty much on top of one another. Now, what's very interesting is that if you look at the integrated metrics for thrust, we're within 3% of CFD, but it only cost us 20% of the computer time that it took to do this CFD one in the middle. And you see we get a lot more of the artifacts, so we can do some tracing of what actually happens in the physics. Next slide, one more. I've got one at just above 1. Now here we don't see any more vortex pairing that goes on, but again, you see very nice predictions just like before. And you also see that we can pick up then the upwash at the rotor hub as well. So we're picking up the same physics that we get from the experiment. In this case, you know, like I said, it was a micro rotor. We're actually trying to repeat this with the X76 rotor. And there's another case done by the University of Glasgow that we're also looking, another student is looking at, and we'll see if the results that we see here hold against scale and against what happens, you know, if you're moving. So this is more for a shipboard approach. Next, please. This is probably my only slide, not from my work in the applications, but I'm very impressed with ART's work. So this is Overflow plus their vorticity velocity particle method. And this is a coaxial rotor, and you see they pick up the helical effect. And again, just like you saw with CHARM, the same thing happens with this particle method. With the long age wakes, you start seeing it breaking up, and it breaks up into little particles rather than the nice vortex lines that you see. But again, if you compare with the integrated quantities, which again, when we talk about a production code, that's a lot of what you want to look at. And you see that they are within slightly high of the measured blade loading, but they are within those bounds. And again, if you're noticing below, I'm giving references. If you want any of these references, I'm happy to send them to you, and I'm happy to send you the Aeronautical Journal paper when it comes out. So next slide, please. We've done a lot of UH-60A development efforts. I'm not going to show them all, but I just want to highlight some. We used the INFAC wind tunnel test data for validation. We looked at high thrust and high speed. We did a very large parametric study to look at best practices. Brian and some of the others have sat through all of these before, but we looked at rotor plus fuselage, rotor, fuselage, and wind tunnel floor. We did a joint paper with Sikorsky, where we looked at dissimilar rotor blades on one rotor. We've also examined using this data set, dynamic stall. We're looking at transition and turbulence models. This is part of the US-French IPA. Most of that data is not yet released, so I can't show it because we have an NDA until we do joint publications. But I do want you to know that we are looking at a lot of different applications here. So next, I want to highlight a couple of results. So next slide, please. Just quickly, we want to talk about our mesh savings. So, you know, here's the baseline. We started with 32 million. Then we brought it down to 20.9, and 20.2 million, where we got a total savings, you know, of the background mesh. And these are about around 40% mesh savings. So keep that number in mind. So you could save 40% just on the mesh. So let's go on and look at the next slide. I want to just show you a quick snapshot of some of the aerodynamic and different loads. So you'll see here, we're not perfect. You know, we're not matching up with the experimental data. This wasn't the point of this exercise. The point of the exercise was to see how close we came to our full overflow simulation. And what you'll see here is that with the exception of the hybrid 3 code, which is where we really started reducing points on the actual surface, that we're almost identical to the full CFD. You know, if you eyeball it, which a lot of people do, say, hey, it looks identical, that's good. We didn't want to just eyeball it. We actually did a number of analyses with Cipher. I'll show you one of those in just a couple of minutes. So one of the important points here is I want you to look at the normalized pitching moment in the middle. Now, the pitching moment is the one that prior solvers have had a lot of problems with, but you'll see here, it's hard to tell, but you'll see that the full CFD, hybrid 1 and hybrid 2, it looks like a reddish green line. Those three are all superimposed, and you can't really tell the difference because they're all so close. Every once in a while you'll see a little bit, but look at that pitching moment. In some of the earlier ones, you know, they would get within 5% of the normal force, but then they would be, you know, 30 to 40% off in the pitching moment. Here we are getting, you know, within 1 or 2% of all of the forces and moments. Next slide. The structural loads, the same thing. Prior to that, we saw some problems in capturing these loads and these bending moments. Here, once again, you see that with just a few little differences, primarily the hybrid 3, they're almost all on top of one another. Now remember, this is about 40% savings in mesh size. Everything else was the same in terms of time step and everything. So next slide. Now we wanted to look at the accuracy, and I'm going to do this with the structural loads because I think this is important. So we use Cipher. I know it's a handling qualities tool, but I think it could be really good for analyzing our CFD data, especially when we're trying to determine, you know, how many harmonics have we well captured? Because if we're trying to do the higher harmonics, we really, you know, we'll plot them, but we'll say, hey, there's this difference, but we don't really see a total change. Now, this gives us, the reason I like Cipher is this gives us both the magnitude and the phase lags. So we can see not just the magnitudes, which is typically what we plot, but we can also see how out of phase they are to whatever we're comparing. Now here we're comparing against the Overflow alone, the full one, and you see that again. Now here the green dashed one is that mesh that was probably too sparse. Number 2, which is the one that we decided was the optimized mesh, is in blue. Now what you see is that the lower harmonics are captured extremely well, but you start losing fidelity at some of the higher harmonics. So, you know, you may, I would say, for example, for chord bending moment, we're probably okay to about 10 per, depending on what your measure of accuracy that you need. And for flat bending moment, we're starting to lose fidelity at about 8 per. It comes back, but then it goes away again. So there's some oscillation there, but this gives you some confidence on what you can expect from your loads. You do have to compare it with something else, but if you have validation data, you know, that will help you design your best practices so that you can do this and look at what you want from your accuracy. Next slide, please. We have hub loads, and hub loads is another thing that other predictive methods have had trouble with. And again, I just wanted to show you it's pretty much on top of one another. And here, you know, this is with a slightly different spacing than before, but this is basically hybrid 2 with some going back and forth. Just, you know, you get the large one and then now you're going small. Next one, please. Again, too, you see that we pick up the physics, the blade vortex interactions. You'll see the large blue that on the original CFD, that's from the outer meshes, those are gone now, and it's replaced with hybrid, with the charm. So you see that that's not there. But if you look and see the magnitudes and the interactions, even in the the fourth quadrant, you'll see a little vortex loop. That's predicted as well. So, you know, having the wake setup does very well. Next slide, please. One thing I want to mention on the prior ones is that we saved 40% on the mesh, but we also found that we had to do approximately 33% revolutions to get to our common goal of convergence, which looked both at the deltas as well as the rate of convergence. So, you know, it converged, you know, in 2/3 the time, and that's because the wake was set up early. And this was particularly true on the high thrust case. Now, we've also looked at rotor fuselage interaction, and you'll see here that we do a good job. I was running out of time, and so I didn't want to put too many more slides here, but you can see that the charm wake actually does come down and predict this. If you look at the paper, it's very close. And it's definitely within the range of what you could do with a regular CFD code, but again, at a fraction of the cost. Next, please. We've done ship air wakes. Now this is with Vortran M, because this is one of those situations where the wake interaction includes a lot of viscous interactions, so shear flows. And so we wanted to demonstrate Fun3D and Vortran M. And we show that we predict the velocities from experiment very well, no matter whether we're using Fun3D or Vortran M. You know, they're either on top and some are closer than others. So I'll let you be the judge of which one's more accurate. But we were very pleased with this result, and so was the Navy. And in fact, the Navy is funding a lot of these efforts now. Next, please. Overflow plus charm and Helios. Guess what? You can run Helios with Overflow charm now. And here's just a movie with that same vehicle that we showed before. And now that flow chart now has little pink things added to it, which shows where we connect with Helios. It's very simple. The coupling routine was written by one of my PhD students who's a smart scholar. He's going to go to Navier, and he'll probably be working as part of the CREATE team up there. And so he will be monitoring this, and he's written this coupling routine so that we'll be able to couple, you know, Fun3D or KCFD, and we can couple other things besides charm. For example, our coupling routine doesn't need to be just charm. It can be Vortran M. It can be whatever code you like, as long as it's written in the correct API. Next, please. Current future development and applications. We're looking at coax and multiple rotors. We've demonstrated we're about to get some validation data from the Navy. We're working on Fun3D plus charm for distributed electric propulsion for NASA. So again, what should we be modeling? There's an awful lot of rotors to be modeled. Do we want to do those full CFD? Can we use actuator blades or actuator lines or actuator discs? What are the trade-offs? We're also doing some work with a CGE, which is a code. It's a CFD code by CDI, and Vortran M2 for regions of high turbulence. We're actually doing this for wind farms. We're developing how to successfully pass turbulence characteristics between the codes and how to keep them, so that, you know, if we come back from charm and we want to go back into CFD, how do we pass turbulence back? We're looking at applications in high gust and transient environments. I'm very interested to know if there's any applications that industry needs, because most of this is funded by the government. But if there's industry applications you want to see, I would really like to know. Next slide. Like to acknowledge a ton of people and a ton of projects. Lots of students have worked on this. We've had a lot of support from the DoD, from Continuum Dynamics, from Richard Brown, and from many industry folks, including you all at Sikorsky, as well as Bell and Boeing. So thank you very much, and I'm happy to take any questions if you could stick around.
Marilyn, thank you so much for presenting this evening. And thanks to all those who participated in putting all of that data together. That was very interesting and informative. We do have a couple questions coming in. The first question is from Fernando Nieves. Is RCAS a type of dual solver?
No, RCAS is a structural dynamics solver. It's the Army structural dynamics solver. Is comparable to NASA's CAMRAD and Olivier Bachot's DIMOR codes. That would provide you your aeroelastic simulations. And for the UH-60, those were aeroelastic simulations. They actually, some of them used DIMOR. I think some of them may have used RCAS. We've moved from DIMOR to RCAS here at Georgia Tech.
Okay, great. We do have one more question for you from Fernando, and he asks, what can we do, what we do, or can we do CFD using just a single blade for hover, no matter what is the type or configuration of the rotorcraft?
Yes, and we prove this out inside of our new code, because that's something if you want to maximize your results in hover or axial flow, where you maybe aren't interested in fuselage interference effects and you just want the rotor, yes, you can do it with one rotor blade. We just don't want to be limited to that. That's the issue. You don't want to be limited to that.
Okay, another question from Vishal. What is charm and what other scenarios can it be applied for?
Sorry, I should have introduced that. So charm is a potential weight code. It's a commercial code from Continuum Dynamics. It's my understanding that it's used at most of the OEMs, including Sikorsky, I believe. Maybe Brian knows for sure. But you can use it alone, and it is used alone in a lot of early applications. And when you have to run many simulations, you can run charm very quickly, in minutes. Now that it has a fast multipole method, so you can run on multiple cores, and it runs very quickly. The problem is you have portions of your flight envelope, or when you're redesigning something, and your physics cannot be picked up by full potential. And that's what we're doing here with the dual solvers.
Okay, we've got another question from Janoslav. Can a U.S. citizen get your software to try out for eVTOLs? And if yes, how can they get it?
Yes, so you need to go through NASA to get Overflow, or we're actually, like I said, when we're done, we should have a beta version of Fun3D Charm probably at the end of this year that we're willing to share. You have to get Charm or Vortran M if you want to use those from Continuum Dynamics. The NASA codes are free. So is Helios if you want to use it within Helios. I'm not sure of the rules for that for eVTOL if it's not for a DoD project. The coupling you get from us. So you have to go through 3 people right now. Once my student Alex graduates and goes to the Navy, then it'll probably be an official Helios release. And then once we're done, when it's done, but you'll be able to get it from NASA and CDI as well. But right now you have to get the coupling from us. But we'll be happy to help you use it.
It's Great. We have one more question, Marilyn, and this is again from Vishal. You had mentioned earlier that a simulation was run with 448 million nodes. Just curious to know how long it takes to obtain the results.
Let me see. That was on there, but let me double check and I'll pull off the number for you.
So yeah, I can answer that a little bit. So that'll depend on how many CPUs you use.
Yep.
These clusters you could run on 400, 800, or 1,000. For some of the larger cases, depending on how much you grab, a case like that would take 1 to 2 weeks instead of a couple days for some of the more production cases.
So for this particular excuse me, for this particular simulation, the cost was 122,880 core hours. And again, as Brian was mentioned, it depends on how many processors and cores you throw at it. Our simulation, the one that was contiguous, that was very good results, cost 14,400. Again, you divide by the number of cores. The non-contiguous full mesh costs 2,000.
We have a couple more questions if you're still good to go.
Sure.
Next question comes from, and I know I'm going to mispronounce this, Byung Young, and he asked.
BY. We go by BY, yeah.
Yeah.
I am glad to see that you have made good improvement in the hybrid method. Regarding computational time, how long does it take for a typical hover simulation, and does it scale well with core number?
So I think we just answered part of that. So depending on if you use the contiguous mesh versus the reduced mesh, it costs 14,000 core hours down to 2,000 core hours. Scaling, yes, it scales very well. The limitation on scaling is basically based on the CFD solver. So, you know, for example, Overflow typically doesn't scale well when you have less than about 100,000 points per node. Charm is not limited. Charm scales quite nicely. But you have to look at how your CFD solver scales. That's going to be the limiting factor there.
Okay, and Vishal has one more question for you, Marilyn. Can the dual hybrid solver be used to analyze hypersonic flows?
A hypersonic helicopter. You know, no. The Overflow certainly can, but yeah, these potential methods, I don't know that they've ever tried to use them in hypersonics. I'll ask Glenn Whitehouse, but my answer is yeah, no, probably not. There's a different suite of approaches in hypersonics that one would use. Different physics require different methodologies if you're going to couple.
Yeah.
Well, that looks like all the questions for you this evening. So thank you again for your time. We really, really appreciate it. I'd also like to take this opportunity to thank Chris Thompson, our VFS headquarters IT person, for his technical expertise in ensuring that these webinars run smoothly. This webinar will be posted on the VFS YouTube channel. And also for everybody attending, please keep your eye open for the VFS lifting competition that will be coming up in the next month. So thank you all so much.